Hi everyone, today a video in the Thermodynamics series looking at entropy. So a reaction that takes place by itself is said to be feasible or spontaneous. What we really mean by that, if you think about spontaneous, you just do it naturally. We're thinking about a reaction that has a tendency just to happen by itself. We don't have to do anything for that reaction to happen. We don't have to put any energy in for that reaction to take place. So exothermic reactions are feasible. This idea that exothermic reactions give out energy from our system to the surroundings, we don't have to put any energy in to make that reaction happen. It will just happen. So it's a feasible or spontaneous process. And a negative enthalpy change that we have for an exothermic reaction is a factor in why these reactions are feasible. But it doesn't explain why some endothermic reactions are feasible. And in the previous video of this series, we looked at some solution enthalpy problems, and we saw from an example that sodium chloride, actually when we worked it out, had a positive, an endothermic enthalpy of solution. What that was telling us is it's potentially not going to dissolve. However, we know that sodium chloride obviously does dissolve. And so the reason why some endothermic reactions are feasible, the reason why they happen spontaneously without us having to put energy in, even though they are an endothermic process where energy has to be taken in by their enthalpy change, is because of entropy. And entropy essentially is to do with how disordered a system is, how random the system is. And so endothermic reactions may be feasible, they may be spontaneous, and those words are just used interchangeably, if they involve an increase in entropy. Now, what do we mean when we talk about how disordered or how random a system is? Well, there's many different ways that we can define this for chemical systems. If we think about the picture that we've got right at the top of this screen, we have this very highly ordered system. Imagine that to be a kind of ionic lattice. Very, very highly ordered, all the ions in a very specific place, and essentially it's kind of stuck in that one arrangement of all its ions. You can then think about across the arrow, the sort of picture that's on the right there, is it being broken up into its ions, individual ions. Now clearly that picture on the right rather than on the left is a much more disordered and much more random system. Actually what we think about when we think about entropy is how many different ways can we arrange the system. So if we think about our highly ordered, let's say it's an ionic solid, the sodium chloride, that's very, very highly ordered. It's not very random at all. It's very, very ordered. And so therefore, how many ways can we arrange that system? Well, actually, we can't arrange it in many ways because it's fixed in that position. If I break it up into its ions, let's say I dissolve it up into solution, well, now it's a much more disordered, much more random system. And I can arrange that system many, many more ways because the ions are free to move. And so this is actually why our sodium chloride dissolves, even though it's an endothermic enthalpy change of solution, because when we dissolve it we create the ions that are free to move. It's a much more disordered and much more random chemical system. There's much more ways of arranging it, and therefore the entropy increases. Entropy also increases when we go from a solid to a liquid or a liquid to a gas. If we think about our actual states of matter, we've just said that a solid is really not very random at all. It's very highly ordered in where the particles are, and they're stuck in those positions. They can't move, they can just vibrate. As we then go to a liquid, well, a liquid can now freely move. It's not completely free like a gas, but there are still intermolecular forces between these molecules potentially, but it's much more free than it was in the solid. The ions can actually move, or the molecules can actually move around. And then again, we go right up to a gas, where now we have these particles in this picture at the top that are completely free to move from each other. There's no intermolecular forces holding them together anymore, and so therefore they're completely free to move around. And so you can imagine that going from the liquid to the gas, we increase our entropy because now that's an even more random system, a more disordered system. There's more ways of arranging that system. And so entropy is also here in terms of why gases will spread to fill space over time. So if I have a gas in a container, it won't just sit in one corner of that container because of the fact that spreading out and filling the whole container gives it more entropy. So the reason why gases will spread, the reason if I have two canisters of gases and I sort of put a divider in the middle and I remove that, the reason why the gases actually mix together and don't just stay within their own canisters again is because entropy increases. And entropy has this tendency to always increase. And so what we want is for our systems to become more disordered, more random. And so anything that involves mixing two solutions together, mixing two gases together, spreading out, so gases spreading out over a greater volume, solids melting or dissolving, liquids evaporating, anything that we can do to randomize it or disorder our system. Another example that's not chemistry related is imagine, essentially entropy is to do with the probability as well. And we can think about, if I have a truck with bricks on the back, let's say those bricks drop from the back of the lorry, well, they could drop such that they form a nice, perfectly formed wall, all on top of each other. Or they could just end up as a complete mess on the floor, very disordered and random. And which one is more probable? Technically, both could happen, but obviously the disordered one is much more probable than the ordered one. Therefore, we say the disordered one has much more entropy. There's many more ways that these disordered ones could be arranged rather than that ordered one where they're perfectly arranged. And so entropy increases when we melt solids or we dissolve them, when we mix liquids or evaporate them, when gases mix, or simply if we increase the temperature. If we think about a solid, you might think, why does the entropy increase? Well, the entropy increases because as we increase temperature, the particles, they can't actually physically move, but they can vibrate more. That's technically a slightly more disordered, more random system. With liquids and gases, increasing the temperature means that the stuff can move quicker. The particles in that solution can move around quicker. Again, that's a more disordered, random state. It's also if we have more moles of products than the reactants. And you can think about this as just simply having, imagine I have A plus B goes to 3C plus 4D within the same space. By having more products than we had reactants, you can hopefully hopefully see that the products would therefore be more disordered than the reactants. Imagine trying to fit 2 people in a room that then turns into 20 people in the same size room. It's going to be a much more random, much more disordered and chaotic system with 20 people in a room compared to just 2. And so we can then think about actually how we calculate entropy changes. Again, we can talk about entropy changes at standard conditions. That's what that Plimsoll subscript symbol dictates. And the subscript T there is just to denote that it's the total entropy change. And we work this out by doing the products minus the reactants. So it's the entropy of the products minus the entropy of the reactants. Now you'll notice here that we're not going to be dealing with entropy changes in terms of the products and the reactants, but actually pure entropy. And we'll talk about this on the next slide. It differs from entropy slightly. The mnemonic I always use to remember it is sprint. So if we're dealing with entropy, S, it's products minus reactants. And the unit of entropy is joules per Kelvin per mole. So slightly different from, remember, enthalpy was kilojoules per mole. Typically, entropy values tend to be a bit smaller, so we use joules rather than kilojoules, but it's joules per Kelvin per mole. So there's also a temperature element in there because we've said that temperature can affect our entropy change. So here I've given you a table of some standard molar entropy values at 298 Kelvin. So again, the idea of standard, think about what it was like for the enthalpy. If I talk about standard enthalpy, it was at standard conditions. And so standard conditions, 298 Kelvin, 100 kilopascals and 1 mole per decimeter cubed if it was a solution. And so here you can see these entropy values. And obviously you don't have to remember any of these, but there's a few takeaway messages that are useful to have here. The first is that hopefully you can see that generally solids tend to have lower entropies than liquids, and they tend to have lower entropies than gases. This is for the exact reason we've talked about on the previous slide, that the gas has much more entropy, it's much more disordered than a liquid is, and that has more entropy and is more disordered than a solid is. And we can see a few key examples. You've got carbon as graphite or as a diamond in the solid state versus carbon as a vapor. In the gas state, you can see there's a huge increase in entropy there, because there's many more ways that our gas can be arranged. It can arrange all the particles in there, so that it's much more disordered, more random, and therefore higher entropy. We can also see, for example, liquid water and water vapor. The water vapor has a higher entropy than the liquid water for the same reason. Now, we can also show some of this sometimes on a entropy temperature graph. So let's say we were looking specifically at water, so going from ice to liquid water to water vapor and measuring the entropy. What we would see, first of all, we'd start off with let's say we start off at a very low temperature with solid ice, solid water. As we heat it up, we know that the entropy increases on increasing temperature, because while our particles within the ice can't actually physically move, they can vibrate more. The solid, remember, can vibrate around fixed positions, and so our entropy increases slightly because there's now a little bit more randomness, a little bit more disorder in that system. And this will increase to the point where we melt our ice. And you can see on the melting point that we have what's called a discontinuity in our graph. We have this straight vertical line. Sometimes that vertical line bit isn't even shown, and you jump straight from where the solid bit ends to where the liquid bit starts. But you can see that there's a big increase in entropy there. Straight away, instantaneously, a huge increase in the entropy. And that's because our liquid is much more disordered than our solid is. It's much more random. There's many more ways we can arrange all the particles in our liquid state than there is in the solid. Again, we can then heat the liquid. We give the particles of the molecules, whatever species are there, more energy, more kinetic energy. Therefore, they move quicker, and therefore there's a bit more randomness, a bit more disorder in our system. And it increases again until we get to the point where we get boiling. So we go from liquid water here to water vapor. And again, you can see a really big discontinuity, this huge change in entropy on going from the liquid to the gas. This is because, again, our gas is now more disordered than our liquid was. In our liquid, we can move around, but we're still sort of held relatively close together by intermolecular forces. In a gas, those forces are broken and we can just move completely freely. So it's much more disordered, many more ways that we can arrange our particles in that system. Again, we can then heat the gas, and again, we'll increase kinetic energy, increase the entropy as the temperature goes up. But the really key takeaway message is that you can see that the change on boiling is much greater than the change on melting. And this is because a gas is so much more, the change from liquid to gas has a much greater entropy change than solid to liquid, because a gas is so much more disordered than a liquid is compared to a liquid versus a solid. There's also two other things to note that are really important. The first is that entropies for our whatever species they might be are always positive. So remember, when we think back to enthalpy, we talked about enthalpy changes, and they could be positive or negative, exothermic or endothermic. These entropy values are always positive, and we'll come back to why in a second. The second is that these are pure entropy values. They're not like in enthalpy, we talk about enthalpy changes. Here, we're not talking about entropy changes, we're just talking about the pure entropy. Now, the reason we can do this is because we actually have a 0 point, something we can define as having zero entropy. We can't do that for enthalpy, but we can for entropy. Because something that has 0 entropy, it would be a pure substance at 0 Kelvin. Now, the key thing here is really the 0 Kelvin. Ever at 0 Kelvin, absolute zero, there's no energy in our particles. They can't even vibrate. At room temperature, even at a low temperature like room temperature, every particle still has some energy and there's still some sort of vibration going on. But at 0 Kelvin, there would be no energy, and therefore they would not be able to even vibrate or anything. They would be locked in one absolute position. And therefore, because there's only physically one way of arranging our system, the actual entropy of this comes out to be 0. Entropy is the number of different ways we can arrange our system, essentially, how random it is. Well, here we have something that can only be arranged one way, completely a perfectly ordered, completely non-random or disordered system. So that has an entropy of 0, a pure substance at 0 Kelvin. And therefore, we can reference every other species against it. And so that's why we have pure entropy values and not entropy changes. And this goes back to why entropies are always positive. They're always positive because we can't have a negative. It's impossible to have a negative entropy. That would imply that there's a negative number of ways of arranging your system. At the very minimum, there must be one way of arranging a system, and that has an entropy of 0. So we can now look at actually how we calculate our entropy, a particular reaction, our entropy change of our reaction. And so the reaction here that we have is this thermal decomposition reaction here of calcium carbonate as a solid decomposing to calcium oxide, a solid, and carbon dioxide as a gas. Now remember, we're still doing thermochemistry, we're still doing thermodynamics, and so it's really important that we have our equations balanced, and also that we include our state symbols, because obviously, as we saw from the previous slide, The state that we're in depends on the entropy. We're given these entropy values for our particular species here in joules per Kelvin per mole on the right. And we just simply remember our mnemonic sprint. So entropy values, we're looking at products minus reactants. So we just do the entropy of the products minus the entropy of the reactants. So we do our entropy of the products, which is our calcium oxide, 40 joules per Kelvin per mole, CO2, 214 joules per Kelvin per mole, add them together, then take away the entropy of the reactants, 93 joules per Kelvin per mole for the calcium carbonate, and this gives us an entropy change, delta S, of plus 161 joules per Kelvin per mole. So again, one thing just to remember and try not to get confused about is that while we don't talk about an entropy change of our particular compounds or our molecules that we're dealing with, we just talk about actual pure definitive entropy values because we have that zero marker, that zero reference point of 0 Kelvin, pure substance at 0 Kelvin, having only one way to arrange the system. We can work out entropy changes of reaction. So if we do a chemical reaction, what's the entropy change for that? And entropy changes, like enthalpy changes, can be positive or negative. If we get a positive entropy change, we've increased the entropy, we've increased the disorder, we've increased the randomness. There's more ways of arranging these products than there were of arranging the reactants. If we decrease our entropy, then we've got a negative number, it's less random, less disordered, or more ordered, you can think of it, and therefore there's less ways of arranging the products than there were the reactants. Now, what we've just calculated here actually is the entropy change of the system. In previous videos of the Thermodynamics and Energetics series, we've talked about this idea of the system and the surroundings. That the system is the actual chemical reaction we're dealing with, the actual chemical entities, and our surroundings is everything else. So here we've calculated the entropy change of the system. This is what we've calculated from our entropy values because it relates to the actual chemical reaction going on, the actual system. However, what we need to consider is our total entropy change. We have to consider the fact that there'll also be an entropy change of the surroundings. If we go back to our enthalpy, think of an exothermic reaction. Heat energy is lost from the system, but that heat energy goes into the surroundings. And so that's why we feel, for an exothermic reaction, we feel things warm up because the surroundings have got hotter, but the actual system must have got colder because it's lost heat. And so our entropy change is the combination of the two. Here we have our entropy change being the same thing, that we have to consider the entropy change in the system and also the corresponding entropy change of the surroundings. The problem is the surroundings are much more hard to define. We said that our surroundings is everything else, everything other than the actual chemical system we're dealing with. So it's literally everything else. So it's much more difficult to define and much more difficult to measure. But we'll see that we can actually get around this issue on the next slide. The final thing just to bring up, and this is a bit advanced for A-level, but just to help you maybe understand it, is a couple of formulae for entropy. So if we're thinking about entropy from a kind of probability, sort of statistics point of view, we have this equation that the entropy, S, is equal to Kb, that's the Boltzmann constant, it's just a number, just a constant, multiplied by the log of this symbol called omega. Now, omega actually stands for the number of ways that we can arrange our system. So I've been talking about the number of ways we can arrange the products or arrange the reactants, and that's why I said that a gas has a much higher entropy than a liquid, which has a much higher entropy than a solid, because there's more ways that our system can be arranged. There's more places the particles can be in different arrangements and stuff. And so if that omega value is greater, the entropy value is greater. It also explains why we talk about our entropy being 0 at 0 Kelvin for a pure substance. Well, if I have a completely pure substance, so no impurities, just a pure substance, one type of atom at 0 Kelvin, so there's no energy, the particles can't even vibrate, there's actually only one way that system can be arranged. It's fixed in that completely ordered arrangement. And the log of 1, the natural log of 1, is 0. And that's why we have a 0 entropy. That's why we have our 0 point that we can define everything to. The other equation that's useful to bring up is if we're thinking about it from a more thermodynamic point of view, we can define the entropy change of our system to be the heat change divided by the temperature. So we can work out another way to work it out would be to work out what our heat change is and divide that by the temperature at which we've done this reaction. Now this is going to be useful for the next slide where we look at a way to get around it, because we can define our surroundings entropy change as being the negative heat change divided by the temperature. And the reason for this is because simply the heat, let's say it's an exothermic reaction, our system will have lost heat energy, there'll be a negative heat change, but that heat must have gone in to heating up the surroundings, and so therefore it's the negative heat change, negative delta Q. Now these equations we don't necessarily need to actually probably use, depends on your exam board, so just double check. But if you're interested in, on the next slide, we're going to look at something called Gibbs Free Energy. The derivation isn't required for A level, but this bottom example of how we can write the system and the surroundings entropy change is important for how we derive it. So if you're interested, you can look that up for yourself, but those are the starting points of the equations that we use. And the trick that we do to get around this is to derive an equation that we call the Gibbs Free Energy. Now the derivation of this obviously isn't required for A level, but essentially what this derivation does is it allows you to express the entropy change of the surroundings in terms of properties that relate to the system, which we do know, we can calculate. And by doing that, and by doing some sort of algebraic manipulation, we end up with this equation for the Gibbs free energy. And so our Gibbs free energy is given the symbol delta G, and then we have that delta G is equal to delta H, our enthalpy change of reaction, minus T delta S, that's the temperature, multiplied by the entropy change of the reaction. Now the key thing is here that in this reaction every single quantity relates to the system, not the surroundings. So by working out this Gibbs free energy, we don't at all have to think about the surroundings at any point. We just have to calculate stuff using the system, which is much more easy. So our enthalpy change is of the system, our entropy change is of the system. Now it's important to watch the units for this. Gibbs free energy is typically given in kilojoules per mole. It has the same unit as enthalpy, kilojoules per mole. Temperature for this has to be in Kelvin. It can't be in degrees Celsius, it has to be in Kelvin. Remember that to get from degrees Celsius to Kelvin, we add 273. And remember that entropy is in joules per Kelvin per mole. And so we just have to make sure that our units match. We can't have things in kilojoules and things that are in joules. We have to pick. So if you're calculating delta G, either convert your delta H into joules, have the entropy in joules, and that would give you your delta G in joules, or convert your delta S into kilojoules per Kelvin per mole, and then that will give you your delta G in kilojoules per mole. Essentially, the unit that you have on your delta H and your delta S has to match. It's either joules or kilojoules for both. Now what we say here is if delta G is negative, that it's a spontaneous reaction, a feasible reaction. This is a reaction that will happen without us having to do anything. If delta G is positive, it's not spontaneous. It's not a feasible reaction. And so we can go back to our calcium carbonate example from before. We've just calculated that our entropy change is plus 161 joules per Kelvin per mole. And we're given here that the enthalpy change is plus 178 kilojoules per mole. Again, we could have predicted that it would be an endothermic enthalpy change. Because this is a thermal decomposition reaction, I'm going to have to put heat energy in to do it. And again, I've just told you here that it's at 25 degrees Celsius because we need the temperature to work out delta G as well. So as I said, either convert the entropy from joules per Kelvin per mole to kilojoules per Kelvin per mole, or convert your enthalpy that's in kilojoules per mole into joules per mole. I always prefer to change my entropy into kilojoules per Kelvin per mole because that gives us our delta G in kilojoules per mole, which is the unit it's most normally required for. So to do that, I have to divide my entropy value by 1,000. So I get 161 divided by 1,000 is 0.161 kilojoules per Kelvin per mole. I then simply put these numbers in, so I put my delta H value in, my temperature and my delta S value in, and I do the calculation and I find that I get my delta G to be plus 130 kilojoules per mole. And what this means, if it's positive, remember, is that it's not spontaneous. This reaction would not happen spontaneously, it would not happen without us having to put any energy in ourselves at 25 degrees Celsius. And so we can draw up a little table here on the right of actually if we have positive or negative enthalpies or entropies, whether that ends up being positive or negative for our Gibbs. And so the two easiest examples to think about is if we have a negative enthalpy change and a positive entropy change. This will give delta G always being negative, because if you think back to the equation, we have a negative number minus a positive number. That's always going to be a negative number. So our delta G will always be negative, and therefore that will always be a feasible reaction. And that makes sense because we have an exothermic reaction, which we know to be feasible, plus a positive entropy change, something becoming more disordered. I said earlier on that there's always a tendency for things to become more disordered, and therefore both of those things help and make it a feasible reaction. The converse is if we have a positive enthalpy and a negative entropy change. So here we have an endothermic reaction where our products are less disordered than our reactants are. If we look back to our equation, we're going to have a positive number minus a negative number. That will always be a positive delta G, and therefore it will never be feasible. And that kind of makes sense. Again, endothermic reaction, we said, tends to not be feasible. The only way it can be feasible is if we have our increase in entropy. Well, here we have a decrease in entropy, and so it's never going to be feasible. And the two other examples where we have either both positive or both negative enthalpy and entropy changes, the key thing is it depends on the temperature. Because essentially, it depends whether our T delta S term is greater than delta H, or if it's less than delta H, because that will determine eventually whether it's a positive or negative delta G. The final thing to talk about is that we can actually also look at Gibbs free energy graphically. So rather than just using the numbers in the equation to work it out, we can actually do it graphically. But the first thing to talk about is that we have our Gibbs free energy equation, delta G equals delta H minus T delta S. Now there will be a specific temperature where delta G actually equals 0. There'll be one specific temperature, one number, where that T delta S term exactly matches the delta H term. So if delta G equals 0, we can therefore say, well 0 equals delta H minus T delta S, and therefore T delta S is the same as delta H. They exactly match. And so we can work out what this temperature will be by rearranging our equation. And so we have T delta S is equal to delta H. We rearrange to find the temperature, divide both sides by delta S. So we have the temperature is delta H divided by delta S. Put the numbers in, and we end up with a temperature here of 1105.6 Kelvin. A very high temperature. Remember, temperature's in Kelvin as well. Now what this actually means, this isn't just a sort of academic exercise of working it out. The temperature at which delta G is 0 is at equilibrium. So this is exactly where we have our calcium carbonate decomposing to calcium oxide and CO2, as well as the reverse reaction of these two reforming the calcium carbonate happening. Remember that our equilibrium is that we have these proportions not changing and the forwards and backward rates occurring at the same rate. They're going as quickly as each other. And so this is the point where we are at equilibrium. When delta G equals 0, it's the point where we're at equilibrium. And you can think about it as kind of like a seesaw. This is the balance point of that seesaw. Going down one way, it's feasible. Going down the other way, it's completely not feasible. But this delta G equals 0 is the balance point. And so if I go to a just slightly lower temperature, it becomes non-feasible. If I go to just a slightly higher temperature, it becomes feasible. And then the final thing to say here is that we can actually do this graphically as well. And so we have our Gibbs equation, delta G equals delta H minus T delta S. Now we can rearrange that, simply just move the two things on the right hand side around and say that essentially we could also write it as delta G is negative T delta S plus delta H. All I've done is just swap the order of those terms on the right hand side. But by doing that, hopefully you can see that it actually looks a bit like the equation for a straight line, y equals mx plus c, where y is what's on our y-axis, x is what's on our x-axis, c is the y-intercept, and m is our gradient. And so by comparing the terms, you can actually plot delta G on the y-axis, you can plot t on the x-axis, and therefore that leaves c being delta H, and m being negative delta S. If you literally just match the terms up. So what that tells me is that I can work all these values out from a straight line graph. That's very easy to work with, very easy to plot and extract data from. And so if I plot my Gibbs free energy change in kilojoules per mole on the y-axis against the temperature on the x-axis in Kelvin, that I'll get a straight line that has a negative slope, a negative gradient, because the gradient is negative delta S. And I know that the point at which this line crosses the y-axis is going to be our enthalpy. So that makes sense. Remember, enthalpy, the enthalpy change and our Gibbs Free Energy change have the same unit. So the point at which it crosses that y-axis will be the enthalpy change. And the gradient, which remember our gradient is our change on the y-axis by our change on the x-axis, is going to be equal to the negative entropy change. So all of these values can actually be worked out from a straight line graph as well. So time to have a go at some questions here. We have this reaction that we can predict the entropy change for, then to actually do it using numbers, and to calculate it at which it would be at thermal equilibrium. The data you need is at the bottom, and so have a go, pause the video, and the answers will be on the next slide. So the equation we're dealing with here is our magnesium oxide is a solid decomposing to form magnesium solid and oxygen gas. And so to calculate the entropy change, we just need to remember our mnemonic, sprint. So we take our entropies and we do products minus reactants. And so we add together the products entropies. Now the key thing, much like with enthalpies, we have to look at our mole ratios. And so if we have 2 lots of something, we multiply it by 2. If we have a half of something, we divide it by 2. And so we have the 32.7 joules per Kelvin per mole of the magnesium plus the 205, but divided by 2 for the oxygen, because it's a half O2 in our equation. We then take away our reactant entropy, which in this case is just the magnesium oxide, 26.9 joules per Kelvin per mole. And this gives us our entropy change as positive 108.3 joules per Kelvin per mole. Now, how could we have predicted this before even doing a calculation? Well, we have 1 mole on the left-hand side going to 2 moles on the right-hand side. That's a more disordered. The products are more disordered than the reactants were. Or we can have the look at the fact that we go from a solid to making a solid and a gas. So because we're making a gas is much more disordered than a solid is. There's many more ways of arranging those particles, and hence we have an entropy increase, an increase in disorder. Then to calculate our Gibbs Free Energy change, so we're given that the entropy change is our 602 kilojoules per mole. Again, remember our units have to match up here. So I'm always going to convert my joules per Kelvin per mole into kilojoules per Kelvin per mole for the entropy change. So my entropy change bit of it is now 108.3 divided by 1000. Temperature is 1000 Kelvin. Remember, it has to be in Kelvin. Entropy change 602 kilojoules per mole. Put all the numbers in and you get your Gibbs Free Energy change to be plus 493.7 kilojoules per mole. Remember that if we have a positive number, it's not spontaneous, it's not feasible at that temperature. And then finally, to calculate the temperature at which we would be at thermal equilibrium, well, this idea of thermal equilibrium is that balance point that I talked about. It's the point at which the delta G is equal to 0. And so if delta G is equal to 0, our equation becomes 0 is equal to delta H minus T delta S. So delta H is equal to T delta S by rearranging that, adding T delta S to both sides. And then we can work out T by just dividing both sides by delta S, such that T is equal to delta H divided by delta S. That then gives us our answer. If we put our numbers in here, remembering that we have to make sure our units match, so both of these are in kilojoules, gives us an answer here of our temperature of 5,558.3 Kelvin. So that's the point where we're at thermal equilibrium. It's the balance point. If I go to just a slightly higher temperature, it becomes feasible. A slightly lower temperature, non-feasible. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found this video helpful, please leave a review on our tuition website. I offer online tuition for chemistry, so please check my tuition pages if you're interested. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.